In this video, we're going to have a look at proofs and some of the terminology that goes around proofs so that we can actually say whether a statement is true or false. Let's start off with a conjecture, which is basically an opinion. In this case, we've got the statement that if x equals 2, then x squared equals 4. This is relatively easy to prove because x equals 2 is only one number. And we know that when we square it, in other words multiply it by itself, we know that 2 multiplied by 2 is equal to 4. What about another conjecture? In this case, the statement is that if a number is prime, then it is also odd. Now, there are lots of prime numbers, and we could probably go through and list many of them. Here are some examples here, 7, 11, 17, and 23, and they're all odd. So it may appear as though this conjecture is true. But we only have to come up with one statement, in this case 2 being prime, which is also even, which contradicts the original statement. This is called a counterexample. And if our original example states or implies that something is true for all values, for example in this case it's saying that every prime number is odd, then all we need is one counterexample to prove that the statement is false. Before we have a look at some proofs, let's have a look at some terminology that we may use. Negation is basically saying that some statement is not the case. So for example, what we're saying here is that if x equals 2, the negation would be that x squared is not equal to 4. The converse switches our statement around. So in this case we had that x equals 2 implies that x squared equals 4. The converse is saying that if x squared equals 4, then x equals 2. Now this one is actually false because if x squared equals 4, x is possibly equal to positive or negative 2. The inverse of a conjecture takes both parts, leaving them in the same position, but negates them. So for example, x equals 2 becomes x not equal to 2, and the statement is saying that x not equal to 2 implies that x squared is not equal to 4. The contrapositive is similar to the converse of a conjecture, except what we do is negate each part. So if x equals 2 implies that x squared equals 4, we switch those parts around, but we negate them so that we get x squared not equal to 4 implies that x is not equal to 2. Let's have a look now at two examples of conjectures and decide on the strategy that we may use to actually prove or disprove the statement. In this conjecture we have two trig equations, and it would appear as though the logical thing to do would be to solve the first equation, in other words find the angles theta that make that statement true for sine, and see if those same angles will work for tan theta such that it will equal root 3. We'll assume here that you have some knowledge of using the unit circle. So we know that sine is positive in the first two quadrants of the unit circle. In fact, we know from exact values or using our calculator that the angle theta that makes that true is pi on 3 or 60 degrees. For this example, we'll stick to radian measure. Now our second angle in the second quadrant will be pi on 3 away from the negative x-axis, which gives us an angle of 2 pi on 3. So now what we do is we test those angles in the second part of our conjecture for tan theta. Tan of pi on 3, knowing our exact values, will equal positive root 3. Tan of 2 pi on 3 will be based on the second quadrant where tan is negative, so it's negative root 3. So we've proved our conjecture to be incorrect because the statement sine theta equals root 3 on 2 does not imply that tan theta will equal positive root 3. It might be wise to pause here and have a read of this conjecture prior to us going on and doing the proof. When you read this statement, there doesn't appear to be a logical algebraic means to try and justify the conjecture. So we have three variables and we know that a, b is equal to c. But how we connect that to the second part of the conjecture, in other words a is less than or equal to the square root of c or b is less than or equal to the square root of c, is unclear. So in this particular example, what we're going to do is what's called a proof by contradiction. We do this by looking at the second part of our conjecture and writing the negation for this particular part. We then go through and show that this isn't possible. Let's have a look at how we do it for this particular example. As before, we start with our initial statement that if AB equals C, then the following occurs. This is the negation. It's a greater than the square root of c and b greater than the square root of c. Let's have a look at how we justify that. In our original statement, we have that a is less than or equal to the square root of c, or b is less than or equal to the square root of c. That means that one of them could be less than or equal to the square root of c, or maybe both of them. So in a number line, that looks something like this. Here's the square root of c. We could have a less than or equal to the square root of c by itself, and b greater than the square root of c. Or we could have b less than or equal to the square root of c, and a greater than the square root of c. Or perhaps both of them are less than or equal to the square root of c. Now the negation of that, in other words everything else, is that both a and b are greater than the square root of c. So let's have a look at what happens if a is greater than the square root of c and b is greater than the square root of c. The first thing we'll do is we'll multiply both sides of the inequality by b. Now that's okay, the inequality holds because b is positive. So ab is greater than b multiplied by the square root of c. Now on the right hand side we know that b is definitely greater than the square root of c, that's our assumption. So that means that we can say that ab is greater than the square root of c multiplied by the square root of c. We can say that because b has been replaced by a value that's smaller than it. So ab is greater than the product of the square roots, which is c. But that's a contradiction to our statement that ab is equal to c at the start of our conjecture. So what that tells us is that our negated form of our original conjecture, in other words a greater than the square root of c and b greater than the square root of c, is false. Given that the statement ab equals c is valid, it is possible for positive real numbers for that to occur. That means the only solution must be the original form, which is a less than or equal to the square root of c, or b less than or equal to the square root of c. We've proved by contradiction that the other case is not possible, so the original example must be valid.